Hello everyone, welcome back to my tutorial. In this tutorial, we are going to solve a natural frequency analysis of cantilever beam. We are going to use a beam element for this case. In previous case, we have used a solid element to solve the same problem. But in this case, we are going to use a beam element to solve the same case. So, our material is steel of Young's modulus 210 gigapascal and Poisson ratio is 0.3 and density is 7860 kg per meter cube. Now we are going to model this beam element in Salome. Let's get started. Now just open this Salome here. I'm just opening. This is my Salome file. So Salome meca is the open source free and post processing software, and it has code aster which is good capable to solve thermomechanical analysis. Now we just go to geometry. Now go to the PPT. So now we just want to model this line. So go to Salome meca. Now we can create the point using icon. Just click this one, point construction. Our first point is 0, 0, 0. So just apply it. Second point is 1. Then apply and close. Now just go to fit screen. You can see this is the first point and this one is the second point. Now we just want to create a line using line command. The same line we can take it from new entity basic line. So the first point is vertex 1 and second point is vertex 2. Apply and close. Now we have created the line. You can see here. Now we will create groups for applying the boundary condition. Just right click line 1, go to create group. First we need to create element. So for this we need to apply a cross section. For that we need to create this one is a beam. Apply. Now we just want to fix it the left side. Here we need to fix it. See our problem here, we need to adjust the degree of freedom in X, Y, Z. So we need to fix it here. For that we need to create groups. So fix. Now add this point. Apply and close. So now we have created these groups. Now we can save this file. Go to file, save as, pictures, code aster. I'm saving here. This one. So I'm just saving here. So now I have saved here. Just now we can go for meshing. Just go to mesh model. Now we are in the mesh model. Go to first select this line 1. Go to mesh, create mesh. Now you can see here 3D and 2D which are disabled because our geometry is just 1D. So this 1D is enabled. Now choose wire discretization and choose the hypothesis as local length. I'm just specifying this local length as 0.02. Save OK, apply and close. Now right click this mesh one, compute. Now you can see we have created 51 nodes and 50 edges. So this is the way we have created. Now we have groups of fix and beam. If you want to edit mesh, you just right click this mesh, go to edit mesh. If you want to reduce, you just edit here. You can make it smaller also. Now again we need to compute. Here you can see, so we need to compute again. Just compute. Now you can see only 11 number of nodes and 10 edges. This linear edges. Now close it. Now we can save it. So mesh also we have saved. Now we can go for code aster. So code aster is the aster study. Now we need to choose the version. I just want to use stable version. Choose OK. Now just you can see only the current case and these things are disabled. So right click here. As we have seen the modal analysis previous case in solid model, we have used stage with assistant, but we cannot use for beam element because this assistant doesn't have the beam element case. For that we need to add one by one. Just add the stage. So stage 1. So we need to now you can see these are things are enabled. We need to add one by one. First we need to read the mesh. Go to mesh, read a mesh. So I just naming it as mesh MED format. Save OK. Now I have read the mesh. Now just go to model definition. We need to define the finite element model. Assign finite element. Just click this icon and go to edit. Now we need to specify it everywhere. Go to mechanic. Here our element is beam element. Just scroll down. There are different types of elements there. Here we need to choose beam. So this is Euler beam. PODE. E means Euler beam. T means Timosika beam. So I just want to use this one. Save OK. Here mesh is this one. Save OK. Now here if you want to rename it, just click it here. This one is model. Save OK. Now we have defined the model. Now we just going to go, we need to specify the cross section area. For that we need to use Afikara element. Click this here. This element property, just element prop. So this is a beam element. We need to go for poetry, add, edit. We need to specify the section, what type of circular, code, general, rectangle. Ours is rectangle section. You just see it here, but the length and height both are same value. So just click it here and click it here. So here these things are thickness. E means thickness. We need to specify height and width. For that HY, HZ. These values are 0.1 and 0.1. Now we have rectangle section we have defined. We need to apply to the group. For that take this first point, edit, apply to the beam, save OK. Now we have completed the process. Save OK. Now we can see here, is anything we need to specify? No. Here we have seen model is enabled. Save OK. Now element property we have defined. Now we need to define the material. Go for material tab. First we need to define the material, then we need to assign the material. So first define the material. So our material is steel. I'm just typing steel. So ours is linear elastic material. Take this one, go to edit. So Young's modulus, Poisson ratio and density. For dynamic analysis we need to specify density also. So 210 e power 9 gigapascal, 0.3, this is 7860. Now just save OK. Now scroll down here, anything we need to specify? No. So nothing you need to specify. Everything are material, different types of material. Now just go to OK. Now we have defined the material. Now we need to assign the material to the mesh. Go to assign material, mesh, model. Go to this one, edit, everywhere, steel. OK. Apply. OK. Now we have assigned the material to the mesh. Now there is no function we are going to define here, so just skip this option. Go to boundary conditions. Here we need to assign the boundary condition. So assign mechanical load. So BC. Here we need to specify enforced degree of freedom. Edit. We need to assign to the group of nodes. Edit. Fix. You just choose the fix. Say OK. Here we need to arrest all the degree of freedom. 3 translation degree of freedom and 3 rotational degree of freedom. Just make it 0. So now we have defined the group and we have defined the boundary conditions. Then say OK. Then apply. Here you can see this is the command it will generate at the back. So it will generate the command file. So this will be the command for applying the fixed boundary condition. So this is the command. Then apply, say OK. Now we have created the boundary conditions also. Then we need to calculate mass and stiffness matrix. For that we need to go for assembly. Assemblage. So matrix assembly. First one I'm taking as mass. This is, we can name it any name we can give. I'm just for understanding mass I'm giving. Choose mass meca. Then one more you add it. Rigid. Choose rigid meca. Here there is option rigid meca. Say OK. Now here we have defined mass matrix, rigidity matrix, that means stiffness matrix. What type of model? Here we need to name it. Here num DLL. This is ourselves any name we can give. So this is commonly in code aster we used to use. So I'm just giving the same name. So we need to define the material. We need to define the element property, and we need to define loads. Click it here, boundary conditions. So these 3 things we need to define it in assembly. Based on that only it will generate the mass and stiffness matrix. Apply it. You can see it here, material, element property and model we have defined here, and boundary conditions. These 4 things we need to define. These things are common. Just go to apply, say OK. Now assemblage we have done. The next process is we need to define the solver. So for that go to analysis, calc mode. This is the solver for calculate the modes, that means number of frequencies. So I'm just naming this as modes. First one is rigid. Rigid is nothing but stiffness, rigidity. That is we need to choose rigid. Mass means mass matrix. Choose this mass. These are not required. Options you can tick it as this plus it. If you are not ticking also it will take default. Then you just go for calculate the frequency. Edit. I just want to calculate 15 number of frequencies. Say OK. Just apply it. So this is the solver. So need not to specify anything. Just OK. Now we have defined the solver. Finally we need to save the results for post processing. Go to output. the output results. Just click the set the output results. Need not to specify any name. Click these 3 dots and go to the location where you want to save. The small one, result.rmed. Just OK. Now just go to results, edit, mesh, modes, element property. There is an option called toucham. You just tick this one, make it S. That means all the values, whatever the results is calculating in the analysis, it has to be saved in the post processing. Now just apply, just give OK, make it MBD format, save OK. Now we have set the output also. Now we can save this file, go to history view. So now we have done everything. To check the values, everything, so just go to the folder here. So this is our Salome meca file, HDF file. This is our study file. Here you can see nothing is saved. So after solving, we can check here. Just go to Salome meca, click this current case and click this stage 1 and click this pin. What it will do, it will keep the results and auto refresh. To view the message file in every 5 seconds, make it 5 seconds, click this run. Now it is solving the case. Now you can check the folder. This is our folder, so just wait for a while here. Now here you can see diagnostic job is OK. That means there is no error, so it has solved very nicely. So it is came, the case is done without an error. Now we can go for post processing. Before going for post processing, we will check our folder. So this is our folder. Here you can see this is the output file. So now we have got the result file of 56.2 KB. And go to study 1 files. Here you can see embedded run case. So here this is our solver file folder. Just click the solver folder and here you can see result stage 1. Just click this folder. Here you can see different types of files: export file, log file. This is the mesh file. While solving, it will save every file in separately and it will solve it. And this is the message file. So whatever we are seeing here, this file, export file, log file, message file, these 3 files are these files: export file, message file, log folder. And this is the command file. So whatever the case we have set it as, that will store in this command file. I'm just opening this command file. So debug means nothing but start. Then mesh, reading the mesh in unit 20. The mesh format is MED. Then definition, model definition is, command is affy model. So this is the beam element we have chosen. Similarly, we have specified the property, so beam rectangle 0.1 and 0.1, and material definition is a diffy material, and material, assigning the material is affy material. So this is the way we have assigned. So these things will generate at the back. And boundary condition we are fixing at the one end. This is assemblage to calculate the mass matrix and stiffness matrix. And this is our solver. Calc mode is the solver to calculate 15 frequencies. Then finally we are saving the results and finish. This is finish. So this is the command file. By using the command file, we can run it by using ASTK also. So I'm just closing here. Now we'll do post processing. Now just go for Paraview to post processing. So right click, build in, open, go to Vengat, pictures, code aster. So this is our folder. So our result is this one. Just OK, then apply. So this is our beam. So this is our beam element. Choose this modes displacement. Generate vectors, apply it. Now we can see, so now you can see only values. This is the 15 modes we have generated. This is the first mode, second mode, third mode, fourth mode. One by one we can see it. But if you want to see the deformed shape, go to generate, click this generate vector, apply it. Now you can see warp by vector is enabled. Now just go to warp by vector, just give the scale factor of 50%, apply it. So this is our first mode. To weave in blue and red, go to rainbow, blue, close, this value make it 12. This is our first mode. To see the second mode, this is our second mode, third mode, fourth, fifth, sixth. 6 is the tensile mode. 7 is it's bending like this. 8 is also tensile mode. Sorry, 8 is bending in this way. 9, 10. So by this way we can see the modes. To view the frequency value, same way, just go here. There is a message file. Just right click this message file and scroll down here. Here you can see this is our frequencies. This is first frequency, second frequency. First frequency and second frequencies are 82 and 82. Third frequency is 496. Fourth frequency is also 496. Now we can compare this frequency with the analytical value. So first frequency is 83 we are getting. In beam element we are getting 82. So similarly 83. Here 499 we are getting, here 522. So here the fourth frequency also here you can see 82, 83, almost very closer value we are getting from the finite element analysis. So thank you for watching my videos. In this we have completed tutorial. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.